Hello, friends. We are ready to begin our thermodynamics unit, and we are going to start with something that's called specific heat. And if you're interested in following along, it's in chapter one, section. No, I've said chapter one, chapter 15, section one. All right. Well, let's go ahead and start talking about it. First of all, just a quick FYI, what this is a picture of. I'm going to move my picture over a little bit. This is a calorimeter. If you've never seen a calorimeter before, this is a machine that could be used to determine, for example, the number of calories, say, in a candy bar. You would put the candy bar in the little area that's called sample cup, and then they would zap with the ignition wires. They would start it on fire, in essence. They would burn it, and the heat given off by the burning candy bar would raise the temperature of the water, and then we would see how much the temperature of the water would increase, and that determines how many calories it had. So for example, if you put a different piece of food in there, if you put a piece of lettuce in there instead, you would see that the temperature of the water would barely change because lettuce doesn't really burn, not like a candy bar would burn, or a nut would burn, or some high calorie food would burn. So the temperature is really what's determining how many calories something has. So we got to go through several different ideas before we get to that point, though. That's kind of summing up where we're headed. We're going to do a calorimetry lab today. Okay, so objectives, things we want to be able to do today. We want to be able to define what energy is. We want to distinguish between potential and kinetic energy. You should have done that in junior high, and we did that earlier this semester also, last semester, but we just need to make sure we're clear on that. We need to relate chemical and potential energy to the heat lost or gained in chemical reactions, and you're going to see that in our calorimetry lab this afternoon or evening or whenever you're doing this. You need to be able to calculate the amount of heat absorbed or released by a substance as its temperature changed. And then just a quick review, remember that temperature is nothing more than a measure of the average kinetic energy of particles in a sample of matter. And we learned about that pretty clearly in the gas laws unit. All right. So the nature of energy. Energy, by definition, and this is one of your objectives, is the ability to do work, which is what most of you learned probably in junior high, or the ability to produce heat. Two forms of energy exist, the potential and kinetic, and you already know potential and kinetic. Potential is often the energy of position. So water that's behind a dam and it's just sitting there, has a lot of potential energy. As it travels through, my picture is in the way, as it travels through the system, it has kinetic energy, and that energy is the energy of motion, and it can be used to turn a turbine, and that energy can be collected. All right, more about the nature of energy. The law of conservation of energy states that energy can be converted from one form to another, but, say it with me, it is neither created nor destroyed. This is also known as the first law of thermodynamics. In the diagram here, you see that wood is stored energy, and you probably never think of wood that way, but what is wood? Wood is a plant product. Well, how do plants grow? They're collecting energy from the sun, peeps. I know that's a weird concept. So during photosynthesis, all that energy from the sun is being collected by those little chloroplasts, and it's being converted into carbohydrates, and it's storing that energy. And that's what that pile of wood is. And when we when we ignite that wood on fire, the energy from the sun gets released in the form of heat and light. It's never created nor destroyed. It's just converted into different forms. I think that's cool. But I think a lot of things are cool, and I'm not very cool. All right, so what's chemical potential energy? Chemical potential energy is the energy stored in a substance because of its composition. I'm going to get my picture out of the way again here. So just to make a few points. So this is a molecule of gasoline. So the potential energy is in the bonds of this molecule that you can see. As these molecules get broken, energy is released. And for gasoline, that's quite a bit of energy. Interestingly, however, a piece of pizza or a whole pizza is full of molecules that have those same kinds of chemical bonds. It's got proteins and lipids and nucleic acids, all kinds of things, and your body knows how to break those bonds. As you break those bonds, it releases heat. That's why your body warms up, but it allows you to make ATP and powers all the rest of your systems. And then the other form of energy, just remember the chemical form of energy in batteries. So batteries have chemicals inside them, stored energy, and that energy gets released as we use the batteries. All right, so chemical potential energy is important in chemical reactions. Now I'm going to switch trains of thought for just a second. It's going to feel a little sudden, but heat, what does that have to do with anything? We'll get there. Heat is energy that is in the process of flowing from a warmer object to a cooler object. And we're going to measure heat using the letter Q. Now I will mention that in the lab today, you will see the symbol delta H. I changed it to Q on your lab, but delta H we will bring up tomorrow. So we'll talk about delta H is referred to as enthalpy, and we'll come up with that, and we'll talk about that in a little bit more tomorrow. So Q today, we're going to use Q is used to symbolize heat. So how do we measure heat? Well, there's a picture of a calorimeter. My face is in front of it again, but way that we can measure it. So a calorie is defined as the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. So this calorimeter that we have a picture of here, it maybe has, I don't know, I'll make up a number. It maybe has 100 or 1,000 grams of water. So if the temperature, as we burn that sample that's in the cup, we started on fire, if the temperature increases by 1 degree and we had 1,000 grams of water in there, then we would say there's 1,000 calories in that food. Now, we got to be careful how we say calorie because food calories are a little bit different than the calories we have in chemistry class. So, food, we always use a capital C, which I think is just dorky. A capital C, which in chemistry class is 1,000 little calories. So, food is measured in capital C calories, or it's 1,000 calories or a kilocalorie. So, on your food product, it'll say Snickers bar is 260 calories. That's a capital C calorie. That would really be 260,000 small c calories. All right, and then a joule is the metric system unit of heat and energy, and it is equivalent to 0.2390 calories. And we're going to be doing some conversion factors where we convert. I better get my picture out of the way. I'm just always in the way, everybody. We're going to have to be converting. So make sure you're on top of these conversions, and you might need to write them down. So a joule, the one you're going to go back and forth on, I think, a little bit more often or most often is this one right here, calorie and joule. If you can just remember this one, I think you're pretty good to go. And then you would just do the conversion factors that are here. I'll give you a moment to write it down because you're going to want it. It'll be helpful if you have that. Okay, we're really close to the end. So what is specific heat? Specific heat is something that we can figure out using a calorimeter, and that's why we were talking about the calorimeter. So the specific heat of any substance is the amount of heat required to raise 1 gram of that substance, not necessarily water this time, 1 gram of that substance, 1 degree Celsius. So clearly it's really related to what we were just talking about with the word calorie. So if we take a look over at the table, it says some objects require more heat than others to raise their temperature. And I just want you to be I want you to notice and be amazed by the specific heat of water. It is incredibly high, and that is key to having life on this planet. There are so many things. I hope we've learned that in AP biology. So many things that allow life on this planet, and if they didn't exist or they weren't true, life wouldn't be here. And one of those principles is the idea of the high specific heat of water, which helps control the temperatures on the planet. It is so hard to heat up our oceans. They are heating up, by the way, with global warming. But it takes an enormous amount of energy to heat up our oceans. And so that helps keep temperatures on our planet from swinging to crazy extremes. And then notice the very low specific heats for some of the metals. We're going to look at a lab today that has to do with finding the specific heat of the metal cadmium. All right, and then just kind of wrapping things up here. So the equation for calculating specific heat is Q equals C times M times delta T. What did we say Q was again? Well, Q is going to be our heat absorbed or released. C is the specific heat of the substance. So in today's lab, you won't know C for the cadmium. Well, you might know it, but you have to calculate it. You have to use the data in the video to calculate C, and then you're going to do a percent error to see how close you are. And then M is the mass of the substance in grams, and delta T is the change in the temperature. The video is really good. Oh, you don't need to do this homework. Sorry, tricked you. Your only other assignment today days to do the lab. I guess that's it. As usual, contact me if you have any questions.